Physics is ever present in the world around us. Some of the things that best exhibit the concepts displayed in physics are sports, and golf is certainly no exception. Some of the best golfers in the world, including the likes of Jordan Spieth, Phil Mickelson, and you guessed it, myself, have spent years and years honing their crafts in order to be able to considered the best in the world at what they do. But have they ever took a look at the physics aspect of what they're doing? Probably not. So sit back and relax as Will and I present to you the physics of golf.
Here's a brief overview of our project. In part 1, when we are hitting a ball off of a tee, projectile motion is the main concept in play. We will use kinematics and the kinematics equations to find the time and distance components to figure out how far in the horizontal x direction the ball traveled. In part 2, when we are rolling the ball into the hole, we are dealing with the conservation of momentum, conservation of energy, specifically translational and rotational energy, and the work done by a frictional force. It is worth noting that in this experiment, we used both TrackMan and the SAM Putt Lab, two very accurate data collection devices to help us record information about both the club and the ball near the instant of impact, which would have otherwise been impossible.
Part 1 of this video explains the kinematics of golf, more specifically, how driving a golf ball relates to projectile motion. Projectile motion, sometimes called parabolic motion, is a special kind of motion where an object moves in the x and y directions at the same time and is subject only to gravity after the initial force. This means that there is only acceleration in the y direction and the velocity in the x direction stays constant during the entire motion. With a set of kinematics equations below, you will never again need to go to the driving range on a cold and rainy day to see how far your average drive is. You can calculate your drives from the comfort of home. Using TrackMan, we've calculated the average velocity of a drive is 69.5 meters per second, and the average launch angle is 12.8 degrees. Now, using this, we need to calculate the x and y velocities. So we plug in the average velocity in a cosine, and then multiply average velocity times sine to get y. We get these two values. Now, before we can calculate how far we go, we need to calculate the time the ball takes to go from hitting the ball to reaching the ground. So we can use this kinematic equation, solve it through, and we get that time is 3.12 seconds. Now, since we have the time it takes, we can plug it into this kinematics equation, solve it out, and get that your drive went 231.2 yards.
The first concept of physics involved in hitting a ball with a putter is the conservation of momentum. But we have to know if the collision is elastic or inelastic. So let's take a look.
As you can see from the video, when the putter struck the ball did not begin rolling. Also, the putter and the ball did not stick together, meaning that this collision was elastic. Now, using this equation, we can figure out the initial velocity of the ball after the collision.
Using the data gathered from the SAM Putt Lab and using our conservation of momentum equation, we can figure out that the exit speed of the ball after it leaves the putter face is 2.95 meters per second.
Arguably the most important question in all of golf is, will the ball fall into the hole? That putt that you saw Will make earlier in the video was about 5 or 6 feet in length. So for this experiment, we're going to back that up to something a little bit harder, say something like 10 feet. The best golfers in the world only average to make about 50% of their putts from 10 feet. To figure out if the ball will fall into the hole, the main factor we're going to be looking at is the velocity of the ball after it has traveled the distance of 10 feet. To do this, we're going to use the concept of conservation of energy. The concept of conservation of energy states that if no outside forces act on a system, the initial energy of the system is equal to the final energy of the system. So in this instance, we have several different types of energy in play. We have the translational energy of the ball plus the rotational energy of the ball initially, minus the work done by friction because the grass is not a smooth surface. And that's going to equal the translational kinetic energy and the rotational kinetic energy after it's traveled the distance of 10 feet. And the equation is going to look something like this. After we use the known values and definitions of translational and rotational kinetic energy.
To sink a putt, the ball's equator must get below the lip of the cup. Putt tracking directly toward the center of the cup cannot drop if the ball is moving more than 3.64 miles per hour. Off center by only 1 inch essentially shrinks the hole, reducing the ball's speed limit to only 2.7 miles per hour.
When looking at a golf ball rolling on grass, we have three forces in play: the normal force, the force due to gravity, and the force due to friction. In this case, the force due to friction is keeping the ball from sliding on the grass. For the friction equation, we have the force of friction equaling the kinetic friction constant times the normal force. To find the normal force, we need to set up a Newton's second law equation where the forces in the y direction are equaling 0 because the ball is not moving up or down. Here we have the normal force minus Fg equals 0, and that results in the normal force equaling the mass times the gravity. Because the golf ball is not moving in the y direction, we can set the normal force equal to the mass of the ball times gravity, which equals 0.441 newtons. Now that we have the normal force, we can enter it into the friction equation. Force of friction equals the friction constant times the normal force, and we get that the friction force equals 0.066 newtons.
Now that we've successfully figured out the work done by the frictional force, we need to head back to our conservation of energy equation in order to figure out the velocity of the ball after it's traveled the 10 feet. However, we need to make a few important substitutions in order to have a solvable equation. The first substitution we are going to make is that omega, the angular velocity of the ball, is equal to the translational velocity of the ball divided by the radius. The second substitution we're going to make is that the work done by a force is equal to that force times the distances applied for. The third and final substitution we're going to make is that the moment of inertia of a sphere is equal to 2/5 times the mass times the radius squared. After substituting in these important things, our equation is going to look something like this. It is only going to have one unknown value, that being the velocity after it's traveled the 10 feet. And this equation becomes surprisingly easy to solve.
After we made our substitutions into our conservation of momentum equation and used the definitions of angular velocity and work done by a force to get numerical values, we plugged everything in, and although it looks very complicated, it was very easy to solve because there was only one unknown. And we got that the final velocity of the ball after traveling the 10 feet was 1.55 meters per second, or converted to miles per hour, 3.64. So in fact, that putt would be able to drop if and only if it was aimed directly at the center of the hole.